I'm going to talk about the SpiNNaker Platform. So I'll introduce you to the platform and show you what it's all about. So the first question is, what is SpiNNaker? Let's have a look. So the SpiNNaker Project, the aim is to produce a computer that consists of 1 million mobile phone equivalent sort of processors, and by this we mean ARM processors. I'll go into detail in a minute. The idea of this is then that it's able to simulate approximately 1% of the human brain. Now we've built it, it's actually looking like we might not quite get that far, but that was the sort of aim originally. And we thought this was equivalent to about 10 mice, although I suppose we may be able to simulate 1 mouse at this point. Let's see how that goes. So to look into the application areas that we want to apply this computer to, of course there's neuroscience, so we want to be able to simulate brain areas or whole brains models in an attempt to better understand how the brain works. We also want to look at neurorobotics, so we want to be able to run neural networks in real time so that we can communicate with robotic devices in the outside world. And we also want to look at future computing. So the idea of this is to be able to take the ideas from brain science, from neurorobotics, from any of our simulations that we've done and apply them into new devices. So I don't know how much people know about normal computers. So I'll just have a quick look at what a normal computer might look like. So a computer usually consists of a central processing unit, which might have 2 or 4 cores. These run in the sort of gigahertz range, and they use power in the range of sort of 35 watts to 95 watts for desktop computers. You also get server processors that are running a lot more computing power than this, and they're more power hungry, of course, as well. Connected to this is usually some external memory, so your laptop will have a certain amount of memory, say 4 gigabytes. You might have servers that have 128 gigabytes of RAM. A desktop PC might have something like 16. You've usually got some large storage device, something like a hard disk in your computer, SSD nowadays. This is so it can store things when the computer's turned off, and when you turn it on it can all start up again. And then there's usually some way for this device to speak to the external world in terms of a network of some sort. To look a little bit deeper into this, inside the processor there's often something called cache memory. This is basically a way to speed up the communication between the main memory of the computer and the processing, so it can do the processing a bit faster. It takes a bit of time to talk to the main memory. There's also something called a DMA controller. This is basically a direct memory access controller. So it allows the processor to go and read things from memory, from external devices, while it's getting on with other tasks. It's sort of a co-processor, I suppose you might say. Quite often, nowadays, these computers are networked together. So you create a network of computers that can all work together to do some task. So high-performance computing is often done in this ways. The network infrastructure itself can often run to hundreds of watts as well in terms of how it's communicating with each other. Okay. So that gives you a kind of background into what a normal computer looks like. Now I'll have a look at what SpiNNaker itself is like, because it's a little bit different. Has some similarities, some differences. So on top, this is the top of the chip. What you'd see if you actually had a SpiNNaker board in front of you, you'd see this. Just underneath that layer, there's the SDRAM, so the main memory of the computer, if you like. This is similar to the main memory on a normal chip, normal computer, except it's actually in the chip, essentially. It's wire bonded to the top of the chip. Still a little bit slow to access, like normal main memory, but it is there. And then underneath this layer, we've actually got all the processing. So you can see there's a connection to the SDRAM here. It's 128 megabytes of SDRAM as well, by the way, so that's quite small compared to a traditional computer. We then have 18 processing cores. Now these are running at 200 megahertz, so they're quite slow compared to your gigahertz processors in your normal computer. They have no floating point unit, so this means that you have to do, if you want to do floating point calculations, you have to do them in software. And there's no memory management, so when you're programming these things, it's quite easy to make silly mistakes, unfortunately. So you have to be a lot more careful with them. There's only 32 kilobytes of instruction memory and 64 kilobytes of data memory. So your instruction memory is where you load your program. Now this is going back to things like BBC microcomputers, where they used to have a very small amount of memory to do this sort of thing. But the idea is we've got lots and lots of cores, so we can sort of split the program across multiple cores. The other idea is that this is all low power computing. So I'll talk about that in a minute. The processors also have a DMA controller, so you can read things from the memory. The difference between this and the one found in a normal processor is the normal processor will be fairly automatic in how it runs these transfers from main memory, so the cache is kind of updated automatically, whereas our local memory is completely user controlled, so you can choose when to activate the DMA and then get on with something else, so you have a bit more control over this. Of course, that comes at the cost of knowing when to do this sort of thing. There's also some shared memory which is useful for message passing between the cores. So the local memory on the cores can only be accessed locally to that core. Each core can't access each other's memory. So there's this sort of shared memory that lets you transfer things. There's also the SDRAM, but of course that's a lot slower. There is an Ethernet connection on every single chip of SpiNNaker. However, we only actually ever connect one Ethernet chip on a board to the outside world, and I'll talk about boards in a minute. And then there's also this, probably one of the most interesting parts of SpiNNaker is it's got this router on board. Now this is the way that SpiNNaker chips communicate with each other, so they don't use the Ethernet to communicate with each other, that's just for the outside world. They use this router to communicate. It has what's called 1024 routing entries, and I'll talk about how those work in a minute, but it's quite different from a normal routing architecture. Yes? Yes, sorry, yes. No problem. So the whole chip uses a watt of electricity. So it's not this 95 watts that you're getting on your desktop processor. You're actually using a single watt to do all these different things. So that's communication, that's the transfer of memory, the execution, and that's 18 cores running all at the same time. So it's quite simple. The routing architecture allows us to transfer packets between the chips, and you can send them to multiple destinations at the same time. So to show you roughly how this works on a SpiNNaker chip, we've got we want to transfer, say, from 1, on this chip, on this machine, to these 3 chips over here, 6, 3, 6, 4, and 8, 3. Don't worry too much about the coordinate system. So what we do is we transfer a packet into from the first chip, and it goes along to 2, 1. Now it turns out that if you don't put any routing information on these chips, they just transfer data straight onto the next chip. So in this case, we don't need to actually tell it to do anything, we just let it transfer data. Now it reaches this chip here, which is 4, 1, and now we want to turn a corner, so we want to change the direction of the packets, so we have to actually put an entry in here. We do so, and we can get it to now go to 6, 3. Now at this point, we actually want it to go in 2 directions, and we can do this with the routing entries. So we can actually transmit simultaneously in 2 different directions, and this will go across here, and then it goes across 7, 3 again with no routing entries and reaches these places. So this is done very quickly across the system. It's not happening like you saw it in my presentation here. You can transfer across the whole of a very large SpiNNaker machine in less than a millisecond, definitely, probably at least half a millisecond, probably even less than that. And then this way we do what's called multicast communication. So we're casting from a single place to lots of other places on the board. Okay, so let's have a look at these SpiNNaker boards. Once we form this network, we've then built our own boards of these SpiNNaker chips. So first of all, here on the left is a SPIN3 board, which consists of 4 chips. This is using about 4 watts of electricity when it's fully powered, so it's very little again. It's probably got approximately the computing power of a modern laptop computer, roughly speaking. So it's not hugely better than a laptop, but it's able to do this with 4 watts, which is something your laptop probably can't do. We also have on the right here a large SpiNNaker board which consists of 48 chips. This uses around 60 watts. Probably the same as a traditional light bulb, but I don't know if anyone knows what a traditional light bulb is anymore. So this board is a bit more useful. You can do a lot more with it. The boards have a single Ethernet, as I mentioned, which allows you to communicate with the external world, load up the boards, set everything up. They also, on the large board, we have something called a board management processor. This allows us to actually configure the board directly from outside, so we can turn it on and off, basically turn on and off the SpiNNaker chips. Obviously, the board management processor has to stay on. We can configure the communication between boards, which is done through FPGAs and things of that nature. The boards also allow you to connect external devices, so we have a few external device ports, and this is useful for things like robotics. So, how can we connect these machines together? Basically, between these large boards, we can actually form multi-board machines. And the way to do this is we connect these FPGAs to communicate between the different boards. So if we connect up a board system like this, we can actually build a 3-board machine that looks like this. I'm not talking about the shape of them at this very minute. I'll come to that in a second. It's basically to do with the 6 links. We can form 6 connections between the boards like this. Yeah, so we can communicate across multiple boards now. We can create a bigger machine. This board obviously has holes in it. So the missing chips can be covered by actually wrapping around the edges of the machine. So instead of just connecting the single edges of the boards, we can actually wrap these around. So if we connect up these additional links, which you may have noticed missing in the previous picture, we can actually form a wraparound machine that looks like this. So this is a 12 by 12 made up of 3 boards connected together. So the boards kind of wrap around at the edges and fill in the holes. Think of it that way. You can use either type of machine. They're not actually critically limited to the 3-board, to the wraparound machines or not wraparound. You can do not wraparound machines perfectly well. So, okay, let's look at what we can make out of these machines at this point. So we can build a 24-board system that looks like this. So we build a rack of boards. And now these are quite tightly packed together. We can then get 5 of these systems into a cabinet like this, so we now have a 120 board cabinet. And then if we wire 10 of these cabinets together, we can form a 1,200 board machine. This is the biggest machine we've actually built to date. It's kind of the biggest the current software supports. It would take some effort to change that. This has a little over 1 million cores. You can see from this animation, this was us booting the machine and counting the cores on it to make sure that we actually had over 1 million cores. We did this live during a session. Clearly I'd practiced it beforehand, but this is not live. This is just a recording of the boot system. It takes a bit of time to do. And you can see there's slightly over 1 million cores in this case. 1,010,300 I think it got to. With cooling, you need approximately 100 kilowatts of power to power the system. Now, the reason for this is that the boards are quite tightly packed together, so we need a lot of cooling in the system as well. So you can probably see all the tubes at the top of this diagram here. They're all connecting the machine to the cooling system, and that takes quite a lot of power to run. But it's still considerably less power than you would need with a traditional computing system of this sort of scale. 100 kilowatts is not bad. We can run it all in a single room. It's quite a small room, actually. Not too bad. We can actually turn the cooling system off as well when the machine is not heavily used. So we do this when we're demonstrating the room, for example. Okay, so we've got this wonderful 1 million core machine, but how can you use it? As a user, you don't want to have to wait while one user is using the full 1 million core machines for your job to run. So what a student has done in the past is made a system which allows us to break the machine up into smaller chunks. The idea is that you ask the server for a small section of the machine. It goes off and queries the machine, finds a bit that you can use, segments it off from the rest, and then your job can actually just go and access that board directly, so you don't have to go via a server once it's running. This does mean you need to be on a machine that's somewhere in Manchester. I'll come to that in a minute as well. The way this works is the user job asks the server actually goes to the FPGAs and cuts off the connections, essentially, from the other boards. Now, this means that your job is completely isolated from other jobs that are running on the system. That means that if you're sending spikes across and something has gone wrong, your spikes won't drift off into somebody else's job, which is obviously a useful thing. You don't want your job interfering with somebody else's. Okay, so with all this hardware, we obviously felt that it was necessary to build some software for users to be able to use it. You don't want to have to go and necessarily understand all that horrible low-level detail. So to do this, we actually built various bits of software. We have a software stack which kind of comes in two halves. One part runs on the machine and one part runs on the host machine, which configures the system. And these communicate over Ethernet, which is the main reason that we have the Ethernet at all. On the SpiNNaker side, we start with low-level C code, so everything's done in C on SpiNNaker. This interfaces with the SpiNNaker hardware at the lowest level, so you don't have to then understand all the hardware bits. You can just call functions in C and it will access the bits of hardware for you. Running on top of this, we actually have a chip monitor system. This is basically the way that this system configures SpiNNaker for you. So when you boot the machine, you load this onto one of the chips, it passes it around the rest of the system, and they all work out where every chip is on the machine. And again, this is used to communicate actually with the host as well then. So once that's booted and running, you can now communicate with SpiNNaker over Ethernet. We'll ignore that, throw that away for now, don't worry too much about it. On top of the low-level library, though, we have an event-driven API. So this further abstracts you from the SpiNNaker code. You kind of now think of SpiNNaker in terms of running events. Events occur, you run one of your functions to process that event. And then at the highest level, we have the application code running. Now, we've written quite a lot of application code already. Again, I'm a software engineer, so I can also say I don't know too much about the neuroscience. But we're also running, we've created all this application code to run for you. So most of the time, you won't have to worry about this horrible detail yet again. This code is already reasonably optimized to run on the system. Okay, so on the other side, the host system, we have, first of all, a communications layer. So, of course, this is the way that we communicate with the machine. We boot the machine, we load things onto the machine, read back your data, everything through this communication layer. Running on top of that is the simulation, control, and execution layer. So this is the bit that basically takes your problem, maps it onto the machine, works out where everything's going to go. I'll come to the detail of that in a bit. And then actually launches your application running on the machine, monitors, make sure it carries on running, and then at the end you can get your data out as well. This is all done by that. And then finally, at the very top level, the bit that you actually interact with is the front-end application. Clearly, we have neural network software. There are other applications as well that we've been playing with. Neural network software is the main bit that you'll probably interact with. In addition to this, the front-end interface is allowed to speak to the communication layer directly, and this is to enable the live interaction with devices as well, which is one of the extra powerful things you get out of SpiNNaker, I suppose, that you don't necessarily get on other platforms. You can interact live from your front end with the actual network running on the machine. Okay, so let's have a look at how the neural network software actually makes use of the chip architecture. First of all, there's your instruction memory. So basically in here, we load your low-level API, your event-driven API, and your application code. That all goes into that instruction memory. So there's not much of it, but we managed to get away with it anyway. There's then your data memory is holding the actual neuron state information. So when you load your neurons onto the machine, they've got things like voltage, they've got various parameters, that all gets stored in there. We also have other things that are useful for that need to be accessed at speed. So things like lookup tables to know where to find things in SDRAM. The processor itself is taking care then of the event handling. So when an event occurs, it's processing that event. It does things like the neuron state update, so it's updating the neuron state as the time goes on in the simulation. It's processing spikes as they arrive so that it knows what to do with them. So the SDRAM actually holds the synaptic states themselves, and the reason for this is there's a lot more of it, so you can now hold more synapses. It also holds recorded data, so recorded data is important in your simulation so you know what went on. And again, it's useful to have a large data store for this, so this is where we store it in SDRAM. We then have our DMA controller, and this is doing the actual transfer between the main memory and the local data memory, so between the SDRAM and the data memory. And then, of course, finally, we have this router, and this is for sending and receiving spikes mainly. That's the bit that you would mostly think of it in a simulation. So let's have a look at the sort of events that we have to process. We have the reception of multicast packets. And in this case, you then have to look up the spike and start a DMA. These are basically controlled by the event-driven API, so this is how we use the event-driven API in our neural code. When a DMA transfer completes, we can then accumulate weights. I'll come into the detail of how we do that in a minute, which can then be used for the neural state update. And then we also have a timer going off, so the timer is periodic, and it tells us to update the neuron every time. So every time the timer goes off, we say, okay, the neuron state is evolving, so we're moving one step to the next in the neuron. We've actually been experimenting with a way of splitting this up. Luca in the audience knows quite a lot about this, where we've been splitting things between synapse processing and neuron processing. So we can actually do the synapse processing on a different core than the neuron processing. This means that the accumulated weights then have to be transferred via the SD-RAM, so from one side to the other. So now we can run the event systems on two different processors on the same system. So how do we actually support weights and delays? Essentially, the packets on SpiNNaker are transmitted, as I said, very quickly between one side and another. So you've got to think, okay, how do we delay a spike from being received or being processed on the core? And the way we do this is we actually have a load of buffers on the core that let us hold the weights as they're received. So if we receive a weight with a delay of 3, we put it in the slot, the third slot along in this buffer. And if we receive one with a delay of 5, we put it in this slot along the buffer. Now, if we receive a second weight with the same delay, we have to add it on. So we add it into the slot. And we can do this because our synapses are modeled using linear models, so we're able to just add on the weights as they occur. Now, what happens if we've got a very big delay? We've only got 16 slots here that we were doing on the processor. So if we've got a very large delay, we actually do this by doing something called a delay extension. And this allows us to take extra 16 slots of delay and do them on a different core altogether. So for a delay of 36, we send them through a delay extension of 32. This then comes to the core, and the core can handle the last 4 slots of delay. And so that goes into the slot 4 as before. But because it's been pre-delayed by 32 time steps, then you don't need to worry about that on the core itself. Okay, so as I mentioned earlier, we've been looking at these alternative mappings. We have the traditional mapping has the neuron and synapses all processed on one core. We also have cores that process Poisson sources, so they would generate Poisson spikes and inject them into the network. And we also have these delay extensions that I mentioned before, so they also take up some cores. Now, in an alternative mapping, we can actually do the synapses and neurons on different cores, and we can actually have multiple cores to process all the different synapses, so that you don't even have to have a single synapse core and a single neuron core. You can have lots of different synapse cores if you've got a lot of synaptic input. The advantage of this is you can actually get rid of the delay extensions because you've now got more local memory to play with on the synapse cores. You get rid of the delay extensions. Great. One thing less. You can also now split your inputs into different cores to do the processing. So you can now handle more spikes on the system. And basically the reason I mentioned this is that when we did the Cortical microcircuit network, we actually did this to get it running in real time. And this is the way we achieved it. By splitting things up, you can now run things in real time that you weren't able to do before. Okay, so what does the host neural network software actually do? So that's what happens on the chip. Let's have a look at what happens on the host. So in the software, we have to basically break up your neural network. So you give us a neural network. You don't describe how it's split up across cores. You just say, I've got populations of neurons. I now want to run that on the machine. Our software has to take that and actually put it on the machine. So it goes, okay, where am I going to put all these things? I'll split the populations down potentially into smaller versions, put them all across different places on the machine. And this might be done in various ways. So it might put different populations on completely different cores or different chips. It might put mixes of populations on chips. So you might get a bit of one and a bit of the other on lots of different chips. You might get bits of your own population, so you split it down into multiple cores, but those cores are actually existing on the same chip, and you're allowed to do that. And again, the software takes care of this for you. It tries to work it out based on connectivity and things like that. Once you've actually done that, you then have to work out how to route the things between the different chips. So again, the software takes this and goes, okay, how do I actually send packets? That diagram I showed you earlier of packets moving across the machine, that is all done by the host software. It works out how to get those packets from one place to the other. Okay, so once we've done that, we then have to load these networks onto the machine. So you've described your populations and your projections. This all turns into data, which is then loaded onto the machine. Simple as that. The largest part of this is the synaptic data. So synapses usually represent most of our data that we're loading. And in the Cortical microcircuit model, we did find that writing that data out took 1.5 hours, and loading that data took 8 hours. So this gives you the sort of scale of data we're talking about here. Fortunately, we've decided that that isn't a good idea, loading all the data onto the machine at the start. So what we now do is we write connection descriptions. So we, rather than actually saying these are the explicit synapses, load those onto the machine, we just say, okay, your connectivity is statistically like this. Load that connection description onto the machine and then let the machine do the work. It's got lots of processors, let it get on with it. This changed the loading, so it changed the generation time from that 1.5 hours to about 1.5 minutes. Significant, and the loading time then is only 1 minute. We do also have to account that then we execute that onto the machine, the actual generation routine, so that's actually now done on the machine, and that took about 3.5 minutes. So that's still 5 minutes down from 9.5 hours, which is a significant change. The other thing that we do, so the idea of SpiNNaker is that we run your simulation in real time. That means that the simulation time runs at the same time as the actual wall clock. So you see the real time, the simulation time are running simultaneously. This isn't all we can do, however. We can actually slow down your simulation. So if there's a very complex simulation, you can actually just say, okay, let's run it a bit slower. Let's run it 10 times slower than real time, for example. So this is more useful for those sort of complex networks. This is what we did with the microcortical column the first time we did it. But of course, we've now managed to run it in real time with all the changes that I mentioned before. The other thing I mentioned was that we support live I/O, and the idea of this is that you might have a robotics device and you want to communicate spikes or commands to that robot device, or spikes from the robot, for example, a retina, and you can feed that in. The software supports describing that connectivity, and you can connect it to various different ports on the board. There are lots of different ways to connect that in. It can go via the FPGAs as well, although that requires some configuration. We also support external communication via the Ethernet, which is a lot easier to do, although it's a bit slower. This can support, for example, spikes being transmitted both into and out of a simulation as it runs. You can also change the rate of Poisson sources, so you can run a Poisson source on the machine and say, okay, I want to change the rate as it goes into the system. And you can also extract membrane voltages from certain models, which you could then do something like to control the speed of a motor, for example. You can say, okay, the membrane voltage is going to do that, which is useful in robotics devices, of course. Okay, so how can you access the SpiNNaker machine? We have a human brain project collaboratory system that basically you can submit jobs. They go into a batch processing system, and the jobs are then run on the machine. So this all runs from servers in our machine room. The servers are sitting alongside the SpiNNaker machine. If you can count on the picture there's actually 11 cabinets, not 10. The 11th cabinet is all our servers. So yeah, but we also have recently started a Jupyter service, and this allows you to then run your networks a bit more interactively, so you can start up and see if things go wrong. You don't get your syntax errors 10 minutes after you've started running the job, for example. This is quite useful. And we also use it for tutorials, so a tutorial happening on Thursday, which we'll be using the Jupyter system. Okay, so that's talked about the actual system. Let's have a look at some usage of the system. So I've already mentioned the Cortical microcircuit model. We've run this in real time. We've also verified that these results are consistent with mnist simulations. So when you run mnist simulations, of course, a lot of people use that as a benchmark of how the system is running. So we've compared ours against that, and we get similar results. We've done statistical analysis, and we get the same sort of answers. We've now also taken on the idea of trying to do the same thing but to run a cerebellum model. So this has actually a similar number of neurons to the cortical microcircuit model, but they're wildly differently split across the system, so it takes quite a different effort to make this work in real time. The reason for this is that some of these cells have to cope with a rather large number of synapses coming into them, so that's an initial complication. But in addition to that, you actually get sometimes 3,000 spikes in a single time step. This is quite a lot for SpiNNaker to have to process. It's not the way we designed the system to cope with it. So we're now, because the system is flexible, we can change what we designed in terms of by changing the software on the system. So we're now looking at writing the software so that it can cope with this high level of input connectivity. On a different sort of approach, we've also had students looking at doing things that are not they're neural, but they're not neural in themselves. So in this case, one of the students modeled the physiological parts of the ear on SpiNNaker. So they wrote models for doing the actual ear processing from taking a sound input and producing spikes at the output. Because this was running on SpiNNaker, it also means that it can be connected to other neural networks that run on SpiNNaker. So you can now have your neural network simulation and your sensor all running on the same platform, interacting with each other in real time, hopefully. On a similar sort of line, we've also had a student look at sensory input using retinas. So they've been able to look at how the photoreceptors connect to the neurons in the network as well. And they've been able to use this to use it as input to the mnist problem. I can show you that in a minute. So that same work used structural plasticity to basically do mnist. And the idea here was that you trained each of the layers. So basically you provided each layer just running structural plasticity. You provide it with all the examples of, for example, a zero. And you can see in the animation here, all the zeros are slowly forming connections on the network, which creates a sort of image map of a zero. You then test the network by feeding all the different layers, one for each of the numbers, the classifiers. You give that a winner takes all, which you can do offline at the end, to decide which of the actual inputs you provide. And this was able to compete sort of reasonably well with mnist algorithms, as far as I know. I'm not sure about the actual output statistics. It's worth reading the paper to find that out, if you're interested. We've also been using structural plasticity to do motion detection. So basically where you're providing moving lines on a screen and you're trying to decide which way they're moving. Are they moving vertically, horizontally? What angle are they moving at, depending on how detailed you want the network model to be. Now at the bottom of this slide, I've shown two different examples. One is where we're allowing delays in the network, and one of them where the delays are all fixed at a single value. And it's basically the one on the left shows us that the delays are critical in this network. And that's an interesting thing because, of course, spiking neural networks involve delays where other neural networks don't. So this may be an important feature of spiking neural networks. Another model that Steve Ferber originally started with, but it was taken on by another PhD student, was to do a sudoku solver on SpiNNaker. So the idea of this is you can connect up the network in using neurons, but you're connecting them up in a way that basically says this number cannot occur at the same time as this number in a square. These are not allowed to occur at the same time in a single position, for example. So you make an entirely inhibitory network. You then have to feed it with some background noise, essentially, because the network is inhibitory. It wouldn't do anything by itself. So you feed it with noise, and it's able to essentially solve Sudoku. I say solve in a sort of high-level sense. It doesn't know what it's doing, so it doesn't stop when it's finished solving. This is a graphical output of it doing a solution of one of the Sudokus. So you can sort of see, in some ways, you can see it jumping around the numbers. Eventually, everything goes green. It's not absolutely guaranteed to stick in that state. It would sometimes go green and then eventually say, oh, I've given up now, I'm going to try something else. And it would start doing other solutions as well at the same time. But yeah, the idea of this was that it could produce the output. We can also see this is a visualization. This was actually produced live output from SpiNNaker. Another thing we're experimenting, because the platform allows you to run things other than neural network code on it, we're also looking at running environments on the system itself. So this is actually a bit of a fake output. Someone actually made this solve breakout. It wasn't actually a trained neural network. Someone did it analytically and worked out how to solve breakout. And the idea here is that the machine essentially plays breakout by itself. But the key point here is the network is running on SpiNNaker. In another side, we can also run environments sort of outside SpiNNaker that you can interact with. So on our Jupyter notebook, we've actually installed the OpenAI gym. So you can then have live input and output from SpiNNaker, communicate with OpenAI gym experiments and say things like Space Invaders and try and solve Space Invaders. We could probably run these platforms on SpiNNaker as well, but it would require someone to write the code to do so. So that's the hard part. And to take this even further, we've also now got the interaction with the virtual neurorobotics environment. So we've made it possible to run SpiNNaker networks, connect them directly to the neurorobotics environment. You just describe your connectivity through transfer functions on the neurorobotics, and it works very much like you use the neurorobotics in any other way. You can see there's an example here of a husky robot that's basically seeing red screens, and it turns around until it sees red, and then it moves towards a red screen. This was an example we took of it running. I can try and show you a live one later if I've got time. It's fairly preliminary work, I should say. The synchronization between the systems, for example, is non-existent. They essentially both run independently as fast as they can. So this could cause problems in the environment in future. So we're looking at this, but you can actually use it through the Jupyter Notebook system already. And then, of course, we've actually got physical robotics. So the pushbot, the TUM pushbot, it was at the time, I'm not sure it's now possibly a Swedish venture instead, is heavily supported. We have access to these pushbots, so we've plugged them into SpiNNaker and we do quite a lot of work with them. There's an example here of a pushbot following a light, for example, so it's turning around when it sees a light. But we can also integrate other robotics devices. It's not restricted to these pushbots. That's what we've worked hard on. But the connectivity is all there, so you can connect it with other devices as well. And to this end, we've also been working with the icub robot. They've been doing a lot of the actual connectivity work here. But we're trying to do a Cerebellum model for the icub to be able to track things. This is not the same as the Cerebellum model we're trying to do in the neuroscience world. This is a robotics Cerebellum model, so it is a bit different. But the idea is that this will also run on SpiNNaker. We also have some non-neural applications. This one's, again, related to neural, but it's not completely neural. And again, it's on the icub. This is doing particle filter on SpiNNaker, and the point of this was that we can use the parallelism of SpiNNaker to process this network, which you wouldn't have been able to do very easily on a CPU. So you can see the scaling on the graph here as SpiNNaker can do more particles in less time, essentially. So you can carry on processing these particles in real time. And again, I don't know much of the detail of the application. I just know the particle filter. If you know what a particle filter is, you might be excited by it. Another application we've been playing with is Markov chain Monte Carlo models. So on a single processor, you can essentially generate lots of samples from your MCMC example. On SpiNNaker, we have lots of processors, so all we do is parallelize it, again, in a very simple way, just explode it across the machine, as many MCMC chains as running as possible. They all start from a totally different place, a random place, and gather lots and lots of samples, and then you can produce far more samples than you could on a PC at the same time. Okay, so a quick look now at what things we're coming up to developing at this point. And the main obvious one is SpiNNaker II. So SpiNNaker 1 has been some 10 years in the production. So we're wanting to produce a modern version of SpiNNaker. There is already a JIB1 test chip, we call it, and this consists of just 8 cores, so it's not even as big as SpiNNaker 1 at this point. But the idea of this is to test out the technology, see what we can do with it. What the actual final SpiNNaker 2 will actually have is 152 cores on a single processor. The aim here is to still run at a single watt, and it's still got the 6 links. So we found the routing architecture of SpiNNaker is actually quite decent still, so we're going to continue with the same routing architecture. We're just going to make it bigger to cope with the number of cores and increased load that we might have on those, and that's just to do with how many routing entries we've got. Of course, to take account of this system, we're also going to have to modify the software. In particular, the low-level hardware API is obviously going to have to be completely different. The chip monitor is probably going to be quite significantly different because it has to deal with the new architecture. There's some things in the architecture that we no longer need to take account of, in fact, so that's quite useful. Could maybe make the chip monitor even lightweight. The event-driven API, because that runs on top of the low-level API, hopefully we won't have to change too much of it. However, there's a good chance we will have to change some bits. We'll have to add in things that are now feature on the new SpiNNaker II chip that are not on SpiNNaker 1. We're also, of course, the communications mechanism across the system is completely different, in fact, so we'll have to rewrite the communication layer in essence. And, of course, we have to change the mapping because the system has more cores, they're split differently. We have to now change the mapping onto this machine quite different.